There's something hidden behind the sun right now, an object scientists call 3I Atlas. Tomorrow, October 29th, it reaches perihelion, the point in its orbit closest to the sun. For most comets, that moment is routine, a brief flare of brilliance as sunlight heats their icy cores, followed by a quiet fade back into the dark. But 3I Atlas isn't like most comets, as it slips behind the sun, creating what astronomers describe as a kind of solar eclipse from Earth's viewpoint. A few curious researchers have begun asking a daring question. What if 3I Atlas isn't just passing by? What if it's here for a reason? It's a thought that echoes one posed by Harvard astrophysicist Avi Loeb since the object's discovery, a question that's fueled debate among scientists and sparked fascination across the world. Could it be possible, even remotely, that 3I Atlas isn't entirely natural? That's the question we'll explore today. Not because we assume it's true, but because in science, the boldest ideas often begin with the questions no one dares to ask. Chapter 1: The Atlas Network. The Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, wasn't originally designed to hunt for objects from other star systems. Its purpose was far more practical: to protect lives here on Earth. 4 telescopes, strategically positioned across the planet, in Hawaii, Chile, and South Africa, work in concert every single night. Their tasks sweep the skies for movement, for anything shifting subtly against the fixed backdrop of stars. Atlas's mission is straightforward, but vital: detect potentially dangerous asteroids early enough for humanity to respond. And by all measures, it's been astonishingly successful. Since its creation, the network has identified thousands of near-Earth objects. Most are small and harmless, posing no danger. But a few, those rare, ominous few, could have been devastating had they slipped by unseen. The process is elegantly simple. The telescopes capture multiple images of the same area of the night sky. Software then compares these frames, pixel by pixel. Any dot of light that changes position between exposures is flagged. Sophisticated algorithms take over, tracking its path, calculating velocity, and projecting its possible trajectory. If the results suggest an anomaly, something that doesn't behave like a typical asteroid, astronomers take a closer look. On the night of July 1, 2025, one of the ATLAS telescopes in Rio Hurtado, Chile, was performing its nightly routine, scanning, recording, and analyzing, when it detected something unusual: an object moving through space. Movement wasn't unexpected, of course. Everything in the cosmos is in motion, but this particular object was fast, far faster than the asteroids ATLAS normally tracks. In fact, far faster than anything gravitationally bound to our sun. Initially, it was tagged as a new asteroid, another moving object to be tracked and logged. But once astronomers examined its velocity data, the classification no longer fit. This wasn't just quick. This was escape velocity quick. To grasp how strange that is, let's set the stage. Earth orbits the Sun at about 30 kilometers per second, roughly 10 to an 8,000 kilometers h, or about 67,000 km/h. Mercury, being closer to the Sun, travels even faster at nearly 48 kilometers h, to keep from falling into the Sun's gravitational grip. Yet, the object that ATLAS detected was clocked at 58 kilometers h, and it was doing that out near Jupiter's orbit, where things normally move much slower. That single fact made astronomers stop. They realized they weren't looking at an ordinary asteroid. When scientists trace an object's orbit backward in time, they can estimate where it originated. Most bodies in our solar system, when plotted this way, trace back to the Sun, bound to its gravity, for billions of years, looping endlessly on elliptical paths. But when they performed the same calculation on this new discovery, the math told a different story. Its trajectory wasn't elliptical, it was hyperbolic, the unmistakable signature of something not from here. A hyperbolic orbit means it's on a one-way trip, entering the solar system once and never coming back. By July 2, 2025, the classification became official. Astronomers added a new prefix to its designation, 3I Atlas, the third interstellar object ever recorded by humanity. A traveler from another star system, Crossing through our own, Chapter 2, The Visitors Before. Before 3I Atlas arrived, there were two others. On October 19, 2017, a telescope in Hawaii noticed something odd. A small, fast-moving object with an orbit that defied expectation. Calculations showed it wasn't native to our solar system. It was the first confirmed interstellar visitor ever detected. The team named it Oumuamua, a Hawaiian word meaning scout. Oumuamua baffled scientists from the start. Its shape was unusual, either long and cigar-like or flat and pancake-shaped, depending on interpretation. It spun end over end in a strange tumbling motion, and most mysteriously, as it left the inner solar system, it accelerated slightly, as if pushed by an invisible force. Avi Loeb from Harvard proposed a daring idea. Perhaps Oumuamua wasn't natural at all, but artificial, possibly a solar sail or fragment of alien technology. The idea ignited controversy. Most astronomers argued that the acceleration was caused by outgassing, jets of vapor released as sunlight warmed, trapped ice, acting like miniature thrusters. The debate, however, changed how scientists thought about interstellar objects. It reminded them that the universe might send us visitors very different from anything we've seen orbiting our sun. 2 years later, in August 2019, an amateur astronomer named Gennady Borisov discovered the second interstellar object with a telescope he built himself. This one was far less mysterious. Designated 2I Borisov, it looked and behaved like a comet, complete with a bright coma and a long glowing tail. Spectroscopic readings showed familiar signatures: water vapor, carbon monoxide, and other compounds typical of comets within our own solar system. If Oumuamua was strange, Borisov was comforting. It hinted that comets across the galaxy might share the same fundamental chemistry and behavior: ice, dust, and sunlight-driven activity, regardless of where they form. Then 6 years after Oumuamua, and 6 years after Borisov, came 3I Atlas. Comparing the three reveals just how unique each one is. Oumuamua was small, perhaps 400 meters long, likely a shard from a larger body shattered long ago, drifting silently for eons. It displayed no visible coma, no tail, just a dark reflective surface spinning every 7.3 hours. 2I Borisov was larger, around 1 kilometer across, clearly a comet glowing brilliantly with vapor and dust, moving at 32 kilometers ants, relative to the Sun. 3I Atlas, however, dwarfs them both. Early estimates placed its diameter around 5.6 kilometers, with newer analyses suggesting it could be even larger, and its velocity, 58 kilometers ants, is nearly double that of the previous two. But speed and size aren't the only oddity. Oumuamua entered from the direction of Vega, diving steeply from above the plane of the solar system, as if tossed over a wall, cutting across the planetary orbits. Borisov arrived from Cassiopeia, again at a sharp angle, from high above the ecliptic. 3I Atlas is different. It's approaching almost perfectly within the ecliptic plane, the flat disk where nearly all major planets travel. Its orbital inclination is just 4.89 degrees. For comparison, Pluto's orbit tilts 17 degrees, and that's considered extreme. That alignment is statistically rare. Space is three-dimensional. Objects could approach from anywhere. The chance of an interstellar visitor arriving within 5 degrees of the ecliptic is less than 0.2%. Some astronomers suggest this might not be as strange as it's. The Milky Way itself is a vast rotating disk, and many stars, along with their ejected debris, travel within that same flattened structure. It's possible that interstellar objects naturally tend to move roughly along the galactic plane, which happens to align somewhat with our solar system's ecliptic. Still, the coincidence is striking, and when combined with 3I Atlas's speed, mass, and trajectory, it adds to a growing list of mysteries, suggesting this latest visitor might not just be another rock passing through the dark. If 3I Atlas truly originated 7 to 10 billion years ago, as its trajectory implies, then it's been traveling through deep space since before our solar system even existed. Across that immense timescale, it would have endured endless waves of cosmic radiation, drastic temperature shifts, and likely countless collisions with other fragments of interstellar debris. Its internal structure, therefore, may be far from uniform, perhaps layered, fractured, and chemically diverse in ways we've never seen in comets born within our solar system. Among the chemical clues astronomers detected, one molecule stood out: cyanogen, a compound of carbon and nitrogen. It was identified in 3I Atlas's coma in early August. At first glance, this isn't remarkable. Many comets contain cyanides and other organic compounds, but when combined with the rest of the comet's chemical inventory, carbon dioxide, water vapor, carbon monoxide, nickel, and various organic molecules, it paints a picture of extraordinary complexity. These substances tell a deeper story. They suggest that 3I Atlas may have formed in the protoplanetary disk of a distant, long-extinct star system, under conditions very different from those that shaped our own. They also indicate eons of preservation in the frozen void between stars, and only now, as it feels the sun's warmth, is it awakening, releasing gases it hasn't vented for billions of years. But chemistry isn't the only mystery surrounding 3I Atlas. Its appearance has proven equally perplexing. Chapter 4. The Tail That Points the Wrong Way. Comets are defined by their tails, that ethereal feature humanity has marveled at for millennia. A glowing nucleus, followed by a long streak of dust and gas, drifting slowly across the night sky. The physics behind it are well understood. As a comet nears the sun, the rising heat causes surface ices to sublimate, turning directly from solid to gas. These vapors, mixed with dust, stream out the solar wind, a constant flow of charged particles emitted by the sun, then pushes this material in a single direction, forming the comet's iconic tail. No matter whether a comet is approaching or leaving the sun, its tail always points away from it. That's basic cometary physics, a rule confirmed through centuries of observation. So when astronomers using the Keck 2 telescope in Hawaii captured images of 3I Atlas in August 2025, they were caught off guard. The comet wasn't behaving like it should. They saw a jet of material pointing directly toward the sun, not a tail, but a tight, concentrated sunward jet stretching nearly 10,000 kilometers from the nucleus. This feature wasn't a random optical illusion. It was real, physical material moving toward the sun. Now, to be fair, so-called anti-tails, forward-pointing features have been observed before, though they're rare and often misunderstood. In most cases, they occur because of perspective. Depending on a comet's orbit and the observer's position, the geometry can make parts of the normal dust tail appear to extend forward, much like how parallel train tracks seem to meet in the distance. But in this case, the evidence didn't fit that explanation. Spectroscopic data confirmed that gas and dust were actually traveling sunward. Something unusual was happening. Astronomers proposed two main natural explanations. First, rotation. If 3I Atlas's nucleus was spinning and had an active vent or fracture aimed roughly toward the sun during part of its rotation, it could create a temporary jet spraying in that direction. As the comet rotated, this jet would sweep across space like a slow-moving lighthouse beam. Second, particle mass. If the dust grains being ejected were unusually large or heavy, they wouldn't respond immediately to solar wind pressure. Instead, they'd keep moving along their initial trajectory for a while, before the sun's force gradually redirected them. This could make the jet temporarily appear to point toward the sun. Both scenarios make sense. Neither requires anything supernatural or artificial. Yet, the timing raised eyebrows. The sunward jet was observed mainly in July and August 2025, when 3I Atlas was still far from the sun, too far for strong solar radiation to dominate its behavior. By September, new observations showed that the jet had vanished, replaced by a normal tail extending away from the sun. That shift made perfect physical sense. Early in its approach, the sun's influence isn't strong enough to immediately sweep the gases back. But as the comet nears perihelion, the solar wind strengthens, overpowering the initial momentum and forcing the tail into the usual anti-solar orientation. Still, the brief existence of that sunward jet invited speculation. In October 2025, Dr. Avi Loeb and his colleagues published a paper proposing a provocative interpretation. What if the directional change represented controlled maneuvering? Here's the logic. If 3I Atlas were not a natural comet, but rather a spacecraft, a sunward jet could function as a braking thrust, an intentional deceleration burn as it approached the sun. The exhaust would appear as a jet pointing toward the star. After the deceleration phase, the engine would shut down, and natural venting of gases would produce a conventional tail. A bold hypothesis, but one that can in theory be tested. If 3I Atlas's trajectory showed non-gravitational acceleration, movement inconsistent with gravity alone during the jet phase, that could hint at propulsion. If the acceleration ceased once the jet disappeared, that would strengthen the case for a deliberate maneuver, but observations to date don't support that. As of September 2025, 3I Atlas has shown no measurable non-gravitational acceleration. Its path aligns perfectly with what Newtonian physics predicts. Gravity alone explains its motion. So, while the sunward jet remains fascinating, all evidence still points to a natural origin, one born of ice, dust, and sunlight, not engines or intentions. However, there's one more fascinating aspect of its tail, a property called polarization. When light reflects or scatters off tiny particles, it becomes polarized, meaning its waves align in specific directions. The degree and orientation of this polarization reveal key details about the particle's size, shape, and composition. Most comets display positive polarization, a typical pattern for sunlight reflecting off dust. But 3I Atlas, it exhibits extreme negative polarization, the most negative ever recorded in a comet. That implies the dust in its coma is unlike anything we've seen before, possibly composed of ultra-fine grains, uniform in size, or made of materials with unusual optical properties. Or perhaps all three. It doesn't break any known rules, but it underscores how alien this visitor truly is. Its dust, its chemistry, even the way it scatters light. All of it hints at an origin story far removed from our own. And yet, studying this interstellar traveler has proven frustrating, because just as astronomers began to understand it, the moment of greatest opportunity slipped away, the moment of its closest approach to the sun. Chapter 5. The Eclipse. October 29th, 2025. Right now, as you read these words, 3I Atlas has reached perihelion, its nearest point to the sun, sitting roughly 1.36 astronomical units away, or about 23 million kilometers from our star. That places it just inside the orbit of Mars. For astronomers, this is the most crucial instant of its entire solar passage. The moment when 3I Atlas is at its most brilliant, its most volatile, and its most revealing. The sun's energy is striking it with maximum intensity, vaporizing frozen materials, and giving us the best possible chance to decode its structure and makeup. But there's a problem. We can't see it, not from Earth. At this exact moment, the arrangement of the solar system hides 3I Atlas directly behind the sun from our perspective. The overwhelming brightness of the solar disk completely obscures any hope of direct observation. This isn't coincidence or misfortune. It's simply the geometry of orbital mechanics. 3I Atlas's path brought it to perihelion on this specific date and hour, and by that same cosmic timing, we on Earth are on the wrong side of the sun to witness it. Ordinarily, this wouldn't matter much. For most comets, we'd lose visibility for a short while, a week or two, then reacquire it once it emerged again. We'd miss the peak observation window. Yes, but still gather plenty of valuable data before and after. But 3I Atlas isn't like most comets, and this particular eclipse, this timing, has sparked more than a few provocative questions. In orbital mechanics, there's a principle known as the Oberth maneuver, named after Hermann Oberth, one of the pioneering minds of rocketry and spaceflight. The concept is straightforward. If you want to change your velocity in the most energy-efficient way possible, you should ignite your engines when you're moving fastest, typically at periapsis, the point of closest approach to a celestial body. Here's why. When you're already traveling at high speed, any additional thrust multiplies your kinetic energy far more than it would if you were moving slowly. It's like accelerating a car already cruising at 100 kilometers per hour versus one at a standstill. The same push generates a far greater increase in momentum when you're already in motion. Spacecraft use this principle constantly. They dive close to a planet, burn their engines at closest approach, and sling outward with far greater speed than a steady burn could ever provide. Now, flip that scenario around. Imagine an interstellar craft entering our solar system at immense velocity. If it wanted to slow down and enter orbit rather than simply slingshot through, the most efficient point to do so would also be at perihelion. Firing thrusters, while moving fastest, relative to the Sun, would yield maximum deceleration for minimum fuel, a reverse orbit maneuver. And here's where things get intriguing. If an intelligent civilization were sending a probe to another star system, and if their goal was to enter orbit rather than perform a flyby, the optimal plan would be to synchronize its arrival, so that this braking burn occurred precisely at perihelion. And if they wanted to conceal that maneuver, to hide the signature of propulsion from prying eyes, they could time it so the perihelion coincided with the object's position on the far side of the target star from the observing civilization. In other words, exactly the same geometry we're witnessing now with 3I Atlas. To be absolutely clear, there's no evidence whatsoever that 3I Atlas is performing any kind of burn or maneuver. Its orbital path remains fully consistent with gravitational dynamics alone. If it were firing engines, even briefly, we'd expect noticeable deviations in its trajectory once it reappears in November. Still, the timing and alignment are striking, enough to fuel debate. One of the most outspoken voices in that debate has been Avi Loeb, who, along with colleagues, proposed in an October 2025 paper titled, "Is the Interstellar Object, 3I Atlas, Alien Technology?" that we should at least consider, as a thought experiment, the possibility of an artificial origin. The paper wasn't claiming proof, but rather exploring how a manufactured interstellar object might present itself and what signs we'd look for to detect it. The authors outlined 7 features of 3I Atlas they found consistent with, though not confirming, a technological nature. Its trajectory lies unusually close to the ecliptic plane, deviating by just 4.89 days, far less than the roughly 45 Dcha average for random interstellar arrival. Its close passes by Venus, Mars and Jupiter, events whose random probability is estimated below 0. The perihelion eclipse from Earth's perspective, perfect conditions for any hidden maneuvering. Its chemical makeup, nickel-rich but curiously lacking iron, a sunward jet that could, in theory, mimic directed thrust, an unusual optical polarization, with a negative reading far stronger than expected, and finally, its sheer size, much larger than previously detected interstellar visitors. Individually, each anomaly could be natural, but the paper argued that taken together, their coincidence was statistically improbable and deserving of closer scrutiny. The authors ended with a carefully worded conclusion, invoking the logic of Pascal's wager. Even if the chance of artificial origin is tiny, the potential consequences of being correct are enormous, too significant to dismiss. The cost of investigating is small. The cost of ignoring a real probe could be historic. Still, most of the scientific community remains skeptical. Tom Statler, NASA's lead scientist for small bodies, remarked, "It looks like a comet. It behaves like a comet. In virtually every measurable way, it matches what we know comets do." Michael Kuppers of the European Space Agency was even more blunt. 3I Atlas acts exactly like a typical comet from beyond our system. Nothing in its behavior requires a more exotic explanation. These reflect the mainstream view, grounded in data, reason, and experience. But Loeb's challenge cuts deeper. It forces science to ask, if an artificial probe did enter our solar system, would we even recognize it? What clues would distinguish it from natural debris? What methods would truly test that hypothesis? Whether or not 3I Atlas is artificial, these questions are worth asking. They redefine how we think about interstellar visitors, and how prepared we are to detect something extraordinary hiding in plain sight. For now, 3I Atlas continues its invisible arc, just beyond our reach, veiled behind the Sun, at the one place where, if it were anything more than natural, it could perform its most efficient and most secretive maneuver. Chapter 6. The Mars Flyby. On October 3, 2025, 3I Atlas made its closest planetary approach of this entire journey, coming within 29 million kilometers of Mars. No other planet would experience a nearer pass during its trek through our solar system. Unlike today's perihelion event, this one was perfectly observable, not from Earth but from a fleet of spacecraft stationed around and upon the red planet itself. For weeks, multiple orbiters and rovers had been preparing for this moment. The European Space Agency's Mars Express and the ExoMars Trace Gas Orbiter, TGO, were aligned to capture it. NASA's Mars Reconnaissance Orbiter, MRO, equipped with the powerful HiRISE camera, turned its lens toward the approaching interstellar traveler. Even the Perseverance rover, sitting on the dusty floor of Jezero crater, aimed its cameras skyward in hopes of glimpsing this visitor from beyond our star system. The first images arrived on October 7. The European Space Agency released data from ExoMars TGO, showing 3I Atlas as a faint, moving speck, just a tiny bright dot drifting against the background stars. Around that dot, a hazy halo of gas and dust, the object's coma, was faintly visible. Capturing these images wasn't easy. The comet was 10,000 to 100,000 times dimmer than Mars's sunlit surface, the very thing these instruments were built to photograph. Yet, they did it. They recorded the first ever images of an interstellar object taken from Mars orbit, the closest human-made observation of such a body in history. Shortly after, Mars Express sent back its own results, similar images, showing a soft, fuzzy glow that shifted slightly from frame to frame. Nothing dramatic to the eye, but scientifically invaluable. The brightness data helped scientists better estimate the object's size and reflectivity, while its subtle color differences offered clues about surface composition. Then came the wait for NASA's HiRISE images. The Mars Reconnaissance Orbiter houses one of the most powerful telescopes ever launched beyond Earth. It can distinguish details on Mars's surface down to 30 centimeters. Aiming it at 3I Atlas, even from 29 million kilometers away, promised the clearest, highest resolution images of the object humanity had ever captured. But as of October 27, 2025, those images still haven't been publicly released. The reason isn't mysterious, just frustrating. The ongoing US government shutdown, which began in late September, has left NASA operating with skeleton crews. Many scientists are furloughed, public communications teams are offline, data processing pipelines continue to run, but public releases are delayed. That delay, however, has ignited predictable waves of conspiracy theories. Social media is buzzing with claims that NASA is hiding evidence that the unreleased HiRISE photos show something extraordinary. Geometric shapes, strange emissions, structures, anything that might suggest 3I Atlas isn't natural. Some even suggest the shutdown itself is a convenient excuse to suppress the truth. The likely reality is far more ordinary. Government shutdowns happen whenever Congress fails to approve funding. During these periods, federal agencies halt all non-essential operations. Public communications are considered non-essential, so while data analysis continues, press releases stop. Still, frustration among scientists is understandable. Dr. Avi Loeb himself expressed irritation in a recent blog post, writing, "Who cares about communication departments? We want the data from the scientists." He's not wrong. The images exist. They've been captured, stored, and are likely being processed right now. The scientific insights won't change whether they're released today or a few weeks from now, but the longer the delay, the more speculation grows. Meanwhile, we do have confirmed data from the Perseverance rover. On October 4th, its Mastcam-Z instrument snapped 2 exposures of the night sky over Jezero crater. When amateur astronomers analyzed the raw files, they noticed a subtle streak of light in the exact region of the sky where 3I Atlas was predicted to be. The streak was faint, barely visible without digital enhancement, but when the images were stacked and brightened, it became clear. A photographer named Simeon Sharp Mice was among the first to post the processed frames online, captioning them, "I think Perseverance may have spotted interstellar comet 3I Atlas last night from Mars. The position matches. The timing matches. The brightness fits prediction." His assessment was correct. The object's alignment, motion, and light intensity all matched perfectly. That faint streak marked the first ever confirmed observation of an interstellar object from the surface of another planet. These Martian observations hold enormous value beyond the spectacle. First, they allow parallax measurements, observations from multiple vantage points millions of kilometers apart. This enables astronomers to triangulate the object's position with exquisite precision, refining its orbital path and velocity. Second, they offer a different angle of view. From Earth, we see 3I Atlas nearly edge-on, its coma partially overlapping its nucleus. From Mars, during its flyby, the viewing geometry shifted, offering a clearer look at the shape and potential asymmetries of its coma features invisible from our planet. Third, they provided behavioral consistency checks. Some theorists who speculated about a possible artificial nature predicted that 3I Atlas might alter course near planetary environments, perhaps avoiding close gravitational encounters. None of that happened. The object's path remained perfectly consistent with pure gravitational motion. No deviation, no signs of propulsion, no surprises. But there's one final detail of this Mars encounter that might prove even more significant. It concerns what's coming next. Two spacecraft currently cruising through the inner solar system, the European Space Agency's Hera mission and NASA's Europa Clipper, are projected, based on recent trajectory models, to pass through the outskirts of 3I Atlas's ion tail. Not the visible dust tail that shines in telescopes, but the second, invisible one, the ion tail. Every comet has two tails. The dust tail, made of reflective particles, is what our eyes and cameras can see. The ion tail, however, is composed of electrically charged gas molecules, invisible to ordinary optics, but detectable by specialized particle sensors. This tail can stretch for millions of kilometers, streaming in a straight, radial line, away from the Sun, under the influence of the solar wind. Based on current models of 3I Atlas's outgassing rate and the solar wind environment, researchers predict that Hera and Europa Clipper will pass through the outer edge of this ion tail sometime between late October and early November. Neither spacecraft was designed for comet science. Hera is en route to study a near-Earth asteroid, while Europa Clipper is focused on Jupiter's icy moon, but their instruments could still record valuable data as they traverse the faint, charged stream trailing from 3I. And when that happens, we may get another unexpected window into the mysteries surrounding this interstellar visitor. Europa Clipper is en route to explore Jupiter's icy moon. Europa, though neither it nor the Hera mission were designed for comet research, both spacecraft carry advanced plasma instruments and particle detectors that study the charged environment of space. If they intersect the path of 3I Atlas's ion tail, those sensors will record it in remarkable detail, capturing the composition, density, and velocity of the electrically charged gas streaming away from the comet. That means we wouldn't just be observing reflected sunlight anymore. We'd be directly sampling material from an interstellar traveler, atoms and molecules released from deep within its core and carried into space by solar radiation. The data, however, won't reach us quickly. Both missions are far from Earth, and their communication speeds are limited. Europa Clipper's readings might not be transmitted back until early 2026, but once analyzed, they could deliver the most detailed chemical breakdown of interstellar matter humanity has ever obtained. Now comes the next chapter, the reappearance. November 7th, that's the date astronomers anticipate 3I Atlas will finally emerge from behind the Sun, visible again to telescopes across Earth. After spending 8 long days completely hidden, its closest solar approach unfolding out of view, it will return, transformed. Perihelion changes every comet. The fierce solar heat awakens ancient ice, vaporizing material untouched for billions of years. Gases explode outward, crusts crack, and dust erupts, reshaping the surface. Sometimes, the object even splits apart. For 3I Atlas, that metamorphosis is happening right now, 23 million kilometers away, unseen. When it returns to view, in early November, astronomers expect dramatic differences. Its coma, the glowing halo of gas and dust, should expand and brighten. The tail may lengthen across millions of kilometers, its luminous arc stretching far behind it. The rate of outgassing will likely surge, and yet subtler shifts may prove even more revealing. If 3I Atlas adjusted its motion during perihelion, even slightly, we'll detect it in its orbit. The object's orbital elements, the mathematical fingerprints that define its trajectory, will reveal any deviation. Around the world, observatories are preparing for this moment. The International Asteroid Warning Network is coordinating a global campaign, not out of fear, but out of scientific urgency. Studying an interstellar object in peak activity is a once-in-a-lifetime opportunity. Their observations will center on precision. Astrometry, exact positional tracking over time, will reveal any non-gravitational acceleration, whether caused by natural gas jets or something harder to explain. Photometry, brightness changes could expose rotation, flares, or fragmenting pieces. Spectroscopy will track the chemical evolution of its coma as deeper layers of its nucleus sublimate. Polarimetry will measure how its scattered light is polarized, revealing details about dust composition and structure. Radar would have provided shape and spin data directly, but at 1.8 astronomical units too distant, radar signals can't return meaningful reflection. The European Space Agency's JUICE spacecraft, the Jupiter Icy Moons Explorer, will observe 3I Atlas between November 2nd and November 12th. Though still journeying toward Jupiter, its vantage point will offer a distinct post-perihelion perspective. JUICE's Janus camera will image the coma, MEGIS will analyze surface ices, SWI will detect molecular gases, and its plasma detectors could even capture stray particles from the tail. Those data won't reach Earth until February 2026, but together they'll create the most comprehensive 3D view of 3I Atlas yet, combining perspectives from Earth, Mars, the Jupiter system, and possibly Europa Clipper's measurements in between. Then comes March 20. One final close approach, 3I Atlas will pass within 54 million kilometers of Jupiter, and NASA's Juno spacecraft, orbiting the gas giant since 2016, will shift its gaze toward it. Though not built for comet studies, Juno carries a rich suite of instruments: JunoCam for color imaging, JURAIM for infrared, UVS for ultraviolet, and MWR for microwave reading. Together they can reveal details invisible from Earth's ground-based telescopes, piercing wavelength our atmosphere blocks. By this time, the interstellar traveler will be cooling again, drifting away from the sun into the deep dark beyond the solar frontier. Its once brilliant coma will contract, and its tail will fade into the black. Yet even as it recedes, 3I Atlas will continue to teach us. Every image, every spectral line, every particle reading adds to the mosaic of what exists beyond our own star, in the cold reaches where comets sleep for eons, preserving the chemistry of their birthplaces. Interstellar comets, as we've discovered, are not uniform. Oumuamua was rocky, dry, and mysterious. Borisov, by contrast, was rich in water and carbon monoxide. 3I Atlas brings another story, one dominated by carbon dioxide, threaded with strange metallic emission. This range of characteristics tells us something profound. Planetary systems across the galaxy form under wildly different conditions. Different stars, different distances, and diverse chemical beginnings yield unique compositions, and when these comets are hurled out of their native systems by gravitational chaos or stellar interactions, they carry the fingerprints of their origin. The Milky Way is filled with such wanderers, cast-offs from countless suns, drifting unseen through interstellar night. Most will never cross our path, but occasionally through sheer cosmic coincidence, and when it does, like 3I Atlas, it offers us a fleeting window into another world, another time, another chapter in the story of the galaxy itself. A visitor from far beyond our solar system, a messenger from another realm, a relic from conditions unlike any we've ever known. 3I Atlas is not just a comet. It's a time capsule forged under alien circumstances, offering humanity a fleeting chance to study material born in a different corner of the galaxy. Even if every oddity about 3I Atlas turns out to have a natural cause, and all current data points in that direction, its existence remains extraordinary. Now let's tackle the question everyone's asking. Chapter 8. The Artificial Hypothesis. Let's talk about the possibility of it being built, not born. Not because evidence demands it, it doesn't, but because respected scientists have raised the question publicly. and repeatedly. Understanding why this question arises and why most researchers reject it reveals something essential about how science actually works. The artificial hypothesis, most clearly articulated by Dr. Avi Loeb and his team, rests on a chain of low-probability coincidences, statistical outliers that, when combined, start to look suspiciously deliberate. Take the first factor, the ecliptic alignment. The odds that an interstellar object would randomly enter the solar system within 5 degrees of our ecliptic plane are about 0. That's rare, but not impossible. Across millions of years and countless interstellar visitors, a few are bound to follow unusual paths. Now, add the close planetary encounters. The chance that a given object would swing within 30 million kilometers of Mars and just 54 million kilometers of Jupiter is roughly 0. Then there's the perihelion eclipse, when 3I Atlas passed behind the Sun from Earth's perspective during its closest solar approach. That alignment isn't especially rare on its own. About half of known comets reach perihelion, while Earth lies on the opposite side of the Sun. But in combination with all these other coincidences, the geometry begins to look strangely purposeful. Next, consider its chemistry. Unusual, even by cosmic standards. Nickel with almost no iron. Intense negative polarization. A composition dominated by carbon dioxide, unlike any other interstellar object we've seen. Each of these traits has potential natural explanations, but all are statistically odd when compared to known comets. Then comes its size, with a nucleus estimated between 5 and 6 kilometers across, possibly even larger. 3I Atlas dwarfs every interstellar visitor observed so far. If such objects follow the same size distribution as asteroids and comets in our own system, we should have detected many smaller interstellar fragments before spotting one this massive. To advocates of the artificial hypothesis, this list of coincidences is too long to ignore. The combined probability of all these traits emerging together in a natural object seems vanishingly small. So small that alternative explanations, however speculative, deserve consideration. Importantly, the hypothesis doesn't claim certainty. It doesn't insist 3I Atlas must be artificial. It simply argues that the natural explanation appears improbable enough that exploring other possibilities is scientifically justified, because if the artificial scenario ever proved true, its implications would be profound. And this, surprisingly, is a fair scientific stand. Science thrives on competing hypotheses. When confronted with an anomaly, scientists don't stop at the first plausible explanation. They outline all possible models, rank them by likelihood, and collect more data to eliminate weaker options. The challenge arises when assigning probabilities without solid baseline data. What's the actual likelihood that an interstellar object could be artificial? We simply don't know. Humanity has never detected alien technology, never confirmed any extraterrestrial artifact, never measured how common advanced civilizations might be, or whether they construct interstellar probes at all. Without this foundation, it's impossible to calculate meaningful odds. Dr. Loeb has informally suggested there's a 30–40% chance that 3I Atlas isn't entirely natural, but these figures are qualitative, intuitive guesses based on perceived anomalies, not statistical rigor. Other experts estimate the odds far lower, 0.01%. But in truth, the numbers matter less than the approach. The essential question is methodological. How should science respond to anomalies when evidence is incomplete? Here's where most scientists converge. Consensus 1. 3I Atlas exhibits multiple unusual traits, making it a worthy subject of intensive research. Consensus 2. Each anomaly can be explained naturally, though some explanations involve rare or unobserved processes. Consensus 3. The combination of these characteristics is statistically uncommon, but not impossible. Consensus 4. There is currently no direct evidence of artificial origin, no radio transmissions, no structural geometry, no unexplained acceleration, no deliberate maneuvers. Where researchers diverge is in philosophy. NASA and ESA take the conservative view. continue treating 3i Atlas as natural until clear evidence says otherwise. This follows the principle of Occam's razor. Favor simple explanations over complex ones. Don't invoke extraordinary causes without necessity. Dr. Loeb's camp argues for a different stance, one rooted in proactive. Even if the artificial possibility is tiny, the potential importance of confirming alien technology would be monumental. Therefore, it deserves serious structured investigation. In his words, we should keep our eyes open and never assume. This tension between skepticism and openness is good for science. It's the creative push-pull that keeps discovery honest. Too much conservatism, and we risk overlooking paradigm-shifting truths. Too much openness, and we chase mirages. History gives us examples of both mistakes. Once dismissed theories like continental drift and bacteria-caused ulcers later proved true. On the other hand, overhyped claims, cold fusion, the EM drive, faster-than-light neutrinos, ultimately collapsed under scrutiny. So where does 3i Atlas fit in that spectrum? Is it another continental drift moment, or another cold fusion detour? As of now, the evidence overwhelmingly points toward a natural object. Here's why. The trajectory of 3i Atlas shows no sign of non-gravitational acceleration. If it were under propulsion or performing controlled maneuvers, its orbit would deviate measurably from a path dictated solely by gravity. But thousands of recorded positions, from May through September 2025, show residuals perfectly consistent with gravitational motion alone. That single observation is the strongest argument against artificiality. Any interstellar craft journeying for billions of years through the void would require occasional course corrections. Space isn't perfectly empty. Microscopic dust, gas molecules, and cosmic rays exert tiny forces that over immense distances would alter its path. A true spacecraft would need to adjust for those disturbances. And yet, 3i Atlas does not. It drifts in silence, obeying only the pull of gravity, as comets do. If 3i Atlas were truly some kind of spacecraft, and if it had any intention beyond simply passing through our solar system, we would almost certainly have seen evidence of active maneuvering by now. Observation 1. The lack of such evidence speaks volumes. Observation 2. Spectroscopic readings align strongly with what we see in natural comets. Carbon dioxide, water vapor, carbon monoxide, cyanogen, and carbonyl sulfide. All these compounds have been observed in ordinary cometary bodies. While the proportions detected are indeed unusual, they still fit comfortably within what's chemically feasible for ices that may have formed under very different conditions elsewhere in the galaxy. Observation 3. There's clear evidence of mass loss throughout gassing. In fact, Dr. Lowe's own models estimate that 3i Atlas has released around 2 million tons of material between July and October 2025. That's entirely consistent with cometary sublimation, the process of frozen gases turning directly into vapor under sunlight. A genuine technological craft would almost certainly have far more efficient methods of managing thermal energy than simply venting vast quantities of gas into space. Observation 4. The object's overall behavior has been remarkably consistent and predictable. Everything from the change in jet direction, shifting from sunward to antisolar, to the increase in water vapor emission, and the pattern of metallic detection, fits perfectly with a comet responding naturally to rising solar heat. No abrupt or inexplicable deviations have occurred that would imply controlled propulsion or guidance. Observation 5. While the close approaches to planets in its path are statistically uncommon, they aren't unprecedented. Within our own solar system, several comets have passed near multiple planets purely by coincidence of geometry. These alignments tend to occur within the galactic plane, the thin disk where the majority of matter, stars and planetary systems in our galaxy reside. Any object ejected from a system in that disk would logically continue traveling within roughly the same plane. Taken together, these observations don't prove that 3i Atlas is a natural object. Science rarely deals in absolute proof, but they make the natural explanation far more plausible than any artificial one. Still, Lowe's cautionary stance remains valid. If we were to dismiss the artificial possibility too quickly and turn out to be wrong, we could overlook the single most extraordinary discovery in human history. So, what would it actually take to tell the difference between a natural object and an artificial probe? Chapter 9: How to Tell the Difference. If a manufactured interstellar craft ever entered our solar system, how could we recognize it? This is no longer a hypothetical thought experiment. With powerful new observatories like the Vera C. Rubin telescope coming online soon, capable of surveying the entire visible sky every few nights, we're on the brink of detecting not just one or two, but dozens of interstellar visitors per year. Eventually, that number could climb into the hundreds. Most of these newcomers will be ordinary comets and asteroids, natural fragments expelled from other planetary systems. But if even one object in a million turns out to be artificial, we must be prepared to recognize it. Lowe has proposed a set of criteria, essentially a checklist of diagnostic tests we can apply. Test 1: Radio emissions. The most straightforward indicator would be radio out. Artificial probes could emit radio waves, intentionally for communication or unintentionally as thermal byproducts of electronics or power generation. SETI teams have already targeted 3I Atlas with radio telescopes, scanning across multiple frequency bands for signals that could not occur naturally. So far, results have been silent. No unusual emission. If the object is artificial, it's either dormant, intentionally non-communicative, or transmitting in ways or wavelengths outside our current monitoring range. Test 2: Trajectory anomalies. Natural bodies obey gravitational dynamics, occasionally modified by cometary outgassing. Artificial ones can maneuver intentionally, altering course, speed, or rotation. To date, 3I Atlas has shown no deviations from gravitational motion. However, it's important to acknowledge a caveat. Small, early course corrections could have gone undetected before sufficient observational data was collected. The crucial test will occur in November and December, when its post-perihelion trajectory can be compared to prediction. If the path deviates more than expected, that would be compelling. Test 3: Surface morphology. Natural objects display irregular forms, jagged edges, uneven albedo, chaotic craters. Artificial objects might show unnatural symmetry, precise angles, or smooth surfaces. Unfortunately, current imaging resolution is insufficient. High-rise cameras aboard Mars orbiters might eventually provide helpful data, but even at 29 million kilometers, the finest resolution would only capture features several kilometers wide, too coarse to detect small-scale engineering details. Test 4: Thermal emission. Technological systems produce heat, either from active electronics or residual decay of radioactive power sources. This could manifest as infrared radiation, exceeding the thermal energy expected from sunlight alone. NASA's James Webb Space Telescope has already observed 3I Atlas in infrared wavelengths, and the results matched perfectly with passive solar heating. No extra warmth detected. That said, a dormant or highly efficient craft could remain undetectable by this method. Test 5: Composition. A natural object's chemical makeup should reflect the conditions of its birth. Familiar ratios of elements and isotopes formed in stellar nurseries and protoplanetary disks. An artificial body might display refined materials, isotopic oddities, or compounds that require technological manufacture. Initially, the detection of nickel without iron in 3I Atlas seemed deeply suspicious, potentially indicating artificial refinement, but subsequent detections revealed trace iron and natural chemical pathways for nickel carbonyl formation were identified, reducing the anomaly's weight. Test 6: Behavioral consistency. Natural bodies follow mathematically predictable light curves and rotational patterns. Artificial ones might act erratically, shifting brightness without correlation to solar distance or abruptly changing orientation. 3I Atlas has exhibited minor surprises, like sudden spikes in water emission or jet direction flips, but all of them can be logically modeled using uneven surface composition and complex sublimation physics. Test 7: Structural endurance. Time will tell whether 3I Atlas can survive perihelion intact. Natural comets tend to fragment under solar stress, their icy matrices cracking apart. Artificial structures might withstand those conditions. If 3I Atlas disintegrates as it rounds the sun, that will strongly favor a natural explanation. If it remains unbroken, that doesn't prove artificiality, but it certainly keeps the conversation open. Test 8. Response to active signaling. This is perhaps the boldest and most controversial idea. If one truly entertains the artificial hypothesis, then communication attempts follow naturally. Some researchers have proposed transmitting radar or laser signals toward 3I Atlas, encoded sequences of prime numbers, universal constants, or geometric patterns to distinguish them from background noise. While the likelihood of any response is vanishingly small, a positive signal would transform everything we know about life in the universe. So far, no one has actually tried this experiment. At least, not yet. As far as current knowledge goes, such a test would be expensive, difficult, and very unlikely to yield a definitive result. But in theory, it could be done. Still, none of these investigative methods alone can conclusively prove that something is artificial. Even if 3I Atlas somehow responded to an attempted communication, there would always be the risk of false positives, natural cosmic phenomena mimicking signals, or human errors in data interpretation. However, if multiple independent tests all produced positive results, say clear trajectory anomalies, detectable radio signals, geometric surface features, and an anomalous thermal signature, then the case for artificial origin would become extremely persuasive. An object displaying all those features simultaneously would be very hard to explain as anything natural. As it stands, 3I Atlas doesn't meet those criteria. Or to put it more precisely, it passes every test in the sense that it looks completely natural by every measurable standard. The artificial probe hypothesis remains possible only in the gaps, in the absence of certain data, or the statistical oddity of some patterns. But the lack of definitive proof of natural origin doesn't automatically become proof of an artificial one. This is exactly where the scientific method matters most. The burden of proof always lies with the extraordinary claim, and the idea that 3I Atlas is a manufactured craft is certainly extraordinary. That kind of claim demands extraordinary evidence. So far, no such evidence has appeared. Every new observation, every fresh data point, pushes the probability further toward natural comet and away from engineered probe. And yet, the question was worth asking, because one day, maybe not with 3I Atlas, but perhaps with another visitor, Object 47 or 23094, or something else entirely, we might encounter a celestial traveler that truly defies natural explanation. When that day comes, we'll need to be ready, with tools, frameworks, and open minds prepared to recognize the signs. Chapter 10. The bigger picture. Whether 3I Atlas is artificial or not, it's already teaching us something extraordinary about our galaxy. It's showing us that interstellar visitors are not uniform. They're astonishingly diverse. So far, we've confirmed only 3 of them, and each has been utterly unique. Oumuamua, small, strangely shaped, accelerating in mysterious ways. Borisov, more typical, a medium-sized comet that looks much like those from our own Oort cloud. And 3I Atlas, large, active, with a complex chemistry hinting that it formed under very different conditions from anything in our solar neighborhood. From just these 3 data points, we can already infer a profound truth. The galaxy produces a stunning variety of planetary systems. Different stars yield different planets, asteroids and comets. Different formation environments create different chemical fingerprints. Different ejection mechanisms fling debris along vastly different paths. This diversity has deep implications for our understanding of planet formation. When scientists study exoplanets, worlds orbiting distant stars, they're limited to indirect techniques. They can measure a planet's mass, size, and orbit. The best instruments can detect certain atmospheric compounds, but they can't yet touch or sample those worlds. Interstellar objects change. Every one that drifts through our solar system is literally carrying fragments of another planetary system. Ice from ancient protoplanetary disks, minerals from shattered worlds, organic molecules shaped by eons of chemistry. By studying these travelers, we're performing interstellar research without leaving home, learning about alien systems through the cosmic messengers they've sent our way. We've already uncovered one of the most reassuring facts imaginable. Water, the essential ingredient for life, seems to be everywhere. Both 2I Borisov and 3I Atlas contain water, and both originated around stars far from the sun. That discovery implies that the building blocks of life aren't rare or localized. They're widespread across the Milky Way. We're also learning that planetary systems can be ancient. The orbital trajectory of 3I Atlas indicates that it may have been ejected from its home system 7 to 10 billion years ago, long before Earth even existed. That means it has been wandering the galaxy since the early days of the Milky Way, carrying within it molecular clues to conditions that existed before our planet was born. It's a deeply humbling realization. We often imagine our solar system as a typical model, a cosmic average. But every interstellar object reminds us how exceptional we actually are. Our comets, for instance, tend to have higher water content and lower carbon dioxide levels than 3I Atlas. Our inner planets are rocky, while other systems may be filled with icy super-Earth. We have a single massive Jupiter in a distant orbit. Other systems host hot Jupiters, skimming close to their stars or none at all. The more we look outward, the clearer it becomes that normal is a local term. What seems ordinary here may be rare elsewhere, and what seems bizarre here may be the standard somewhere else. This diversity is a gift, especially in the search for life. If every planetary system were identical, then life would either arise everywhere under the same fixed conditions, or nowhere at all. But with such diversity, there are countless possible routes for life to emerge, through different chemistries, energy sources, and evolutionary paths. The variety revealed by interstellar objects tells us the galaxy is brimming with potential we've barely begun to imagine. Consider the scale of it all. Our Milky Way contains between 100 and 400 billion stars. Most of those stars have planets. That means there are hundreds of billions of potential birthplaces for comets. Some fraction of those comets will inevitably be ejected through gravitational interaction. Astronomers estimate that each star system might throw out trillions of small bodies over its life. If even a tiny fraction, say 1%, manage to escape completely into interstellar space, that still adds up to an astronomical number. Some calculations even suggest there could be more free-floating interstellar comets and asteroids than those bound to stars. Imagine that a galaxy filled with wanderers, silent travelers drifting between suns, shaped by billions of years of gravitational encounters. And out of those uncountable billions, we've detected only 3. That's about to change. The Rubin Observatory, expected to begin full operations in early 2025, will revolutionize sky monitoring. It will scan the entire visible sky every few nights, capturing anything that moves or changes, from asteroids and comets to supernovae and variable stars. Among those detections will be interstellar visitors. Current estimates predict Rubin could identify 1 new interstellar object every month once it's fully operational, maybe even more. Within a decade, we could have a database containing hundreds of these galactic wanderers. Each will tell a slightly different story. One icy, one rocky, one metallic, one chemically exotic. And perhaps one day, one of them will exhibit traits that simply can't be explained by natural processes. And when that happens, humanity will be ready. This is exactly why Loeb's artificial hypothesis, even if improbable in the case of 3I Atlas, holds profound value for what lies ahead. Humanity needs a reliable framework to recognize artificially created objects long before we stumble upon one. We must define clear detection standards, establish reliable tests, and design swift, coordinated investigation protocols. Because if an engineered interstellar probe ever does cross into our solar system, the clock starts ticking the moment it's detected. These cosmic wanderers move at immense speeds and remain in our observational range only briefly. By the time a consensus forms on what to search for, the visitor may already be gone. 3I Atlas, regardless of its origin, has become a rehearsal, a simulation of how we'll handle such an event. It's showing us what to observe, how to analyze, and how to coordinate rapid global response. The Mars flyby, for instance, proved that humanity can quickly mobilize spacecraft to target and study a newly discovered object. The spectroscopy efforts demonstrated that high-quality chemical data can be gathered in record time. Meanwhile, detailed orbital calculations confirmed that we now have the precision to detect even subtle deviations from purely gravitational motion. We're improving, and will need to. The rate at which interstellar objects are being found is increasing, and with more advanced instruments, that rate will only accelerate. Each new arrival is like a sealed message from another world, a cosmic sample couriered across unimaginable distances. Even if 3I Atlas turns out to be nothing more than ancient rock and ice, which current evidence strongly suggests, it remains extraordinary. It's a relic over 7 billion years old, a frozen messenger from the thick disk of the Milky Way, formed long before our sun ignited, before the Earth solidified, before life began here. For a brief period, in 2025, it wandered close enough for humanity to catch a glimpse, to measure and to learn from, before it vanished again into the endless dark between stars. That's something worth gratitude. Now, let's look at what happens next. Chapter 11, Perihelion and Beyond. At this very moment, 3I Atlas has reached its perihelion, its closest pass to the sun. Its surface temperature is climbing to extremes it hasn't felt in billions of years, perhaps ever. The ice that has been stable for eons is now sublimating at a furious pace. Jets of gas and streams of dust are escaping into space. The coma is expanding outward, the tail elongating, yet ironically none of it is visible to us right now. The comet is positioned behind the sun from Earth's viewpoint, hidden by its glare. This temporary invisibility frustrates astronomers, but it isn't a total loss. Months of previous observations have already yielded a wealth of data about 3I Atlas, its estimated size, its chemical composition, its spin rate, and its emission behavior. What we don't yet know is how this solar encounter will alter it. Some comets endure perihelion largely intact. They lose mass, develop fractures, but remain cohesive and continue on their outbound path. Others, however, disintegrate. The heat-induced stress triggers cracks that race through the nucleus until the body breaks apart. One object becomes several, a loose stream of debris scattered across a widening orbit. Which fate awaits 3I? Its size suggests stability. Larger comets typically endure longer since their greater mass provides internal strength and a lower surface area to volume ratio, which reduces thermal strain. Yet its vast age is a concern. After billions of years drifting in interstellar space, pelted by cosmic rays, micrometeoroids, and cycles of freezing and thawing near various stars, its interior may be fragile, riddled with hidden weaknesses. We'll know more on November 7th, when it re-emerges from behind the sun and becomes observable once again. The first task will be to refine its position. Where exactly is it? Has its velocity shifted? Any noticeable trajectory change could reveal something critical, either fragmentation or non-gravitational acceleration. Fragmentation would cause the remnants to spread into slightly diverging paths, while non-gravitational motion, perhaps from asymmetric outgassing or another unknown force, could nudge the entire body off its expected orbit. Next will come imaging. Astronomers will study the coma, tail and nucleus in fine detail. Has the coma expanded? Has the tail become more structured or irregular? Are there visible fragments or jets? Then comes spectroscopy, the study of its light. Has the chemical signature of the emitted gases changed? Are we now seeing compounds from deeper within the comet's core, exposed by the sun's heat? These rapid synchronized observations will continue intensively, because 3I Atlas will fade quickly as it recedes from both the sun and Earth. By December 2025, it may already require large telescopes to detect. By early 2026, only the most powerful observatories will be capable of tracking it. Its closest approach to Earth occurs on December 19, 2025, when it will still be about 1.8 astronomical units away, roughly 270 million kilometers. That's far beyond Mars's orbit, yet it represents our best vantage point for detailed study from the ground. By that time, the comet will be cooling, its activity diminishing, but still luminous enough for analysis, and ideally placed for Northern Hemisphere observation. For skilled amateur astronomers with telescopes 8 inches or larger, 3I Atlas might appear as a faint, fuzzy glow drifting through the constellation Virgo. It won't be spectacular, no dramatic tails visible to the naked eye, no celestial fireworks, but for those who understand what they're witnessing, it will be a once-in-a-lifetime sight. A visitor from another star system, a relic that has traveled across light years and eons, now shimmering faintly in our night sky before vanishing forever. Professional monitoring will continue through the end of every spectrum recorded, every brightness curve logged, every coordinate noted, will add to our understanding, not just of 3i Atlas, but of the vast galactic environment that forged it. In March 2026, a key event will follow, the Jupiter encounter. 3i Atlas will pass within about 54 million kilometers of the gas giant. NASA's Juno spacecraft, orbiting Jupiter, will be in position to gather data. The European Space Agency's JUICE probe might also capture distant readings, if the timing aligns. While this won't be as intimate as the earlier Mars flyby, the differing perspective will provide fresh insights and a valuable geometric comparison. From there, 3i Atlas will continue its long journey outward, past Jupiter, then Saturn, though not especially close, heading toward the icy outskirts of the solar system. With every passing month, it will fade further, dimming into near invisibility. By late 2026, it will likely vanish from most telescope ranges. By 2027, it will have slipped beyond measurable limits, and by 2030, it will cross Neptune's orbit, entering the boundary where the solar system's light gives way to interstellar night. After that, it will be gone, back into the cosmic silence it came from, carrying with it the scars of its encounter with our sun, the gas it lost, the cracks it gained, the heat it endured. Yet it won't be the same object anymore. It will have been transformed, a traveler forever altered by its fleeting visit to our corner of the galaxy. It will change, reshaped by its fleeting encounter with our star, altered in ways we might anticipate, and in others we can't even begin to grasp. If 3i Atlas is a natural object, and every line of evidence still points that way, then the transformation it undergoes is purely physical. Ice turns to vapor, solid matter dissolves into gas, and the slow, relentless process of sublimation unfolds under the intensity of solar heat. But if 3i Atlas was something more, something engineered, then its transformation could be informational. It might mean data collected, samples stored, mission objectives met or missed. We might never know. Eventually, the object will drift away. Our instruments will lose sight of it, and it will fade into the backdrop of deep space. Just another speck among the stars, bound for another system over tens or even hundreds of thousands of years. Unless something changes, unless its path suddenly shifts this November, unless a faint radio signal cuts through the static, unless the high-resolution images, once released, reveal something that defies explanation. Each of these scenarios is wildly improbable. The odds of any actually occurring are infinitesimal, but that's precisely what keeps science alive. The rare, improbable moments that force us to rewrite what we think we know. The times when our equations break and our understanding must evolve. 3i Atlas has already given us one of those moments, not because it's artificial, but because it's different. Different from Oumuamua, different from Borisov, different from the icy wanderers that orbit within our own system. It's reminded us that we're still students of the cosmos, that planetary systems, comets, and interstellar mechanics still hold secrets we've only begun to uncover. And in its own quiet way, 3i Atlas has prepared us for what's coming next. Chapter 12, The Dark Forest Question. There's a question we've been circling, a question that makes many scientists uneasy, one that feels almost taboo to ask in a formal research setting. Yet, it's been asked, published in preprints, discussed at conferences and in interviews. If intelligent civilizations exist elsewhere in our galaxy, and statistically they almost certainly do, then why haven't we found them? This is the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, over lunch, "Where is everybody?" Given the vast age of the Milky Way, roughly 13 billion years, and the countless stars and planets within it, intelligent life should have emerged long before us. Some civilizations should have developed interstellar technology. Some should have sent probes spanning the galaxy. Yet, there's silence. No radio beacons, no megastructures, no visible signs of large-scale engineering. Just nothing. Over time, dozens of possible explanations have emerged. Maybe intelligence is exceptionally rare. Maybe civilizations self-destruct before mastering interstellar travel. Maybe they're here, just hidden. Maybe they communicate in ways we can't yet recognize. Among the more unsettling theories is the dark forest hypothesis, introduced in a novel by Liu Cixin, but serious enough to deserve real consideration. It suggests that in a galaxy filled with unknown civilizations, all competing for finite resources, the safest move is silence, to hide, to listen, but never because if you announce your existence through a radio broadcast or a massive, visible structure, you make yourself a target. Another civilization might see you as a threat, or as a resource, or simply as competition. In that view, the cosmos is a dark forest, and every civilization is a hunter, silent, watching, and armed. The absence of evidence, then, isn't proof of emptiness. It might be the result of universal caution. Everyone is listening, no one dares to speak, and in the most extreme interpretation, survival might demand preemptive elimination. If a civilization detects another before being detected itself, it might choose to strike first, not out of malice, but fear, self-preservation. This, of course, is speculative, philosophical, not empirical. We have no proof that this is how the galaxy works. It's one of many explanations for Fermi's paradox, and not necessarily the most probable, but it connects intriguingly to 3I Atlas because of a recent hypothesis proposed by Loeb and his colleagues in a July paper. They asked, if a highly advanced civilization wanted to send a reconnaissance probe to our solar system, how would it behave? Their answer: it might look almost identical to 3I Atlas. Such a probe would approach at extraordinary speed, remaining nearly invisible until it was already well inside the system. It would enter from a direction masked by dense star fields, minimizing early detection. It would align itself with the ecliptic plane, allowing flybys of multiple planets. It would time its closest solar pass, its perihelion, for a period when Earth's view was blocked by the sun, masking any maneuvers. And if it followed the dark forest principle, it would observe quiet. It would collect data without transmission, conceal all evidence of artifice, and mimic the randomness of a natural comet. This is, of course, a thought experiment, but such exercises matter in science. They push us to examine unlikely, even uncomfortable possibilities. Still, the hypothesis rests on a long chain of ifs. First, intelligent life must exist elsewhere, plausible, but unproven. Second, at least one civilization must have achieved interstellar travel, speculative, but conceivable. Third, that civilization must have identified our solar system as a target, which requires either immense detection power or blind exploration of countless systems. Fourth, the probe would need to have arrived precisely now, within the short period that humanity has telescopes capable of noticing it. Already, probability shrinks dramatically. Fifth, the probe must appear large and reflective enough to be seen, yet reveal no unmistakable technological features, a contradiction in itself. Sixth, it would have to operate under strict stealth, valuing observation over any communication or contact, a very specific strategic mindset, not guaranteed to be universal. Each link in this chain is uncertain. Together they stretch plausibility, but improbable is not impossible. And sometimes, the improbable is exactly what science exists to explore. It will change, reshaped by its fleeting encounter with our star, altered in ways we might anticipate, and in others we can't even begin to grasp. If 3I Atlas is a natural object, and every line of evidence still points that way, then the transformation it undergoes is purely physical. Ice turns to vapor, solid matter dissolves into gas, and the slow, relentless process of sublimation unfolds under the intensity of solar heat. But if 3I Atlas was something more, something engineered, then its transformation could be informational. It might mean data collected, samples stored, mission objectives met or missed. We might never know. Eventually, the object will drift away. Our instruments will lose sight of it, and it will fade into the backdrop of deep space. Just another speck among the stars, bound for another system over tens or even hundreds of thousands of years. Unless something changes, unless its path suddenly shifts this November, unless a faint radio signal cuts through the static, unless the high-resolution images, once released, reveal something that defies explanation. Each of these scenarios is wildly improbable, The odds of any actually occurring are infinitesimal, but that's precisely what keeps science alive. The rare, improbable moments that force us to rewrite what we think we know. The times when our equations break and our understanding must evolve. 3i Atlas has already given us one of those moments. Not because it's artificial, but because it's different. Different from Oumuamua, different from Borisov, different from the icy wanderers that orbit within our own system. It's reminded us that we're still students of the cosmos, that planetary systems, comets, and interstellar mechanics still hold secrets we've only begun to uncover. And in its own quiet way, 3i Atlas has prepared us for what's coming next. Chapter 12, The Dark Forest Question. There's a question we've been circling, a question that makes many scientists uneasy, one that feels almost taboo to ask in a formal research setting. Yet, it's been asked, published in preprints, discussed at conferences and in interviews. If intelligent civilizations exist elsewhere in our galaxy, and statistically they almost certainly do, then why haven't we found them? This is the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, over lunch, "Where is everybody?" Given the vast age of the Milky Way, roughly 13 billion years, and the countless stars and planets within it, intelligent life should have emerged long before us. Some civilizations should have developed interstellar technology. Some should have sent probes spanning the galaxy. Yet, there's silence. No radio beacons, no megastructures, no visible signs of large-scale engineering, just nothing. Over time, dozens of possible explanations have emerged. Maybe intelligence is exceptionally rare. Maybe civilizations self-destruct before mastering interstellar travel. Maybe they're here, just hidden. Maybe they communicate in ways we can't yet recognize. Among the more unsettling theories is the dark forest hypothesis, introduced in a novel by Liu Cixin, but serious enough to deserve real consideration. It suggests that in a galaxy filled with unknown civilizations, all competing for finite resources, the safest move is silence, to hide, to listen, but never because if you announce your existence through a radio broadcast or a massive, visible structure, you make yourself a target. Another civilization might see you as a threat, or as a resource, or simply as competition. In that view, the cosmos is a dark forest, and every civilization is a hunter, silent, watching, and armed. The absence of evidence, then, isn't proof of emptiness. It might be the result of universal caution. Everyone is listening, no one dares to speak, and in the most extreme interpretation, survival might demand preemptive elimination. If a civilization detects another before being detected itself, it might choose to strike first, not out of malice, but fear, self-preservation. This, of course, is speculative, philosophical, not empirical. We have no proof that this is how the galaxy works. It's one of many explanations for Fermi's paradox, and not necessarily the most probable, but it connects intriguingly to 3i Atlas, because of a recent hypothesis proposed by Loeb and his colleagues in a July paper. They asked, if a highly advanced civilization wanted to send a reconnaissance probe to our solar system, how would it behave? Their answer: it might look almost identical to 3i Atlas. Such a probe would approach at extraordinary speed, remaining nearly invisible until it was already well inside the system. It would enter from a direction masked by dense star fields, minimizing early detection. It would align itself with the ecliptic plane, allowing flybys of multiple planets. It would time its closest solar pass, its perihelion, for a period when Earth's view was blocked by the sun, masking any maneuvers. And if it followed the dark forest principle, it would observe quiet. It would collect data without transmission, conceal all evidence of artifice, and mimic the randomness of a natural comet. This is, of course, a thought experiment, but such exercises matter in science. They push us to examine unlikely, even uncomfortable possibilities. Still, the hypothesis rests on a long chain of ifs. First, intelligent life must exist elsewhere, plausible, but unproven. Second, at least one civilization must have achieved interstellar travel, speculative, but conceivable. Third, that civilization must have identified our solar system as a target, which requires either immense detection power or blind exploration of countless systems. Fourth, the probe would need to have arrived precisely now, within the short period that humanity has telescopes capable of noticing it. Already, probability shrinks dramatically. Fifth, the probe must appear large and reflective enough to be seen, yet reveal no unmistakable technological features, a contradiction in itself. Sixth, it would have to operate under strict stealth, valuing observation over any communication or contact, a very specific strategic mindset, not guaranteed to be universal. Each link in this chain is uncertain. Together they stretch plausibility, but improbable is not impossible. And sometimes, the improbable is exactly what science exists to explore. The universe is vast, unimaginably vast. In a cosmos of this scale, even the rarest possibilities will eventually happen. Flip a coin long enough, and somewhere in that infinite sequence, you'll get 100 heads in a row. The odds of that specific outcome are microscopic, yet not impossible. Something improbable must still occur. So while the dark forest hypothesis as applied to 3I Atlas seems highly unlikely, it remains worth holding in consideration, not as a preferred theory, but as one to be ruled out through evidence, not assumption. The proper way to do that is the same as before: trajectory analysis, spectroscopy, radio monitoring, and surface imaging. We look for anything that cannot be explained by natural processes. So far, everything observed about 3I Atlas fits comfortably within natural expectations. The slight trajectory shift fall within the margins expected for cometary outgassing. Its unusual chemistry still involves compounds known to form in icy bodies. The timing, though coincidental, doesn't defy probability. The dark forest scenario persists only because we cannot prove a negative. We can't definitively prove that 3I Atlas is not artificial, just as we can't disprove the existence of a tiny invisible teapot orbiting Mars. The absence of evidence for artificial origin isn't proof of natural origin, but it's the closest thing we can get. More importantly, constantly invoking the dark forest frame can actually hinder scientific progress. If every anomaly is treated as a possible threat, if suspicion replaces curiosity, we risk overlooking the genuine scientific insights such objects can offer. We could waste precious time and resources chasing ghosts instead of systematically studying interstellar material. Worse, we might unintentionally feed public fear, fears that thrive on uncertainty and distortion. We've already seen this play out. The online reaction to 3I Atlas has been a revealing case study. Alongside real scientific interest came a flood of misinformation, conspiracy theories, apocalyptic predictions, and wild interpretations of legitimate data. Some insist NASA is concealing the truth. Others claim the object is about to veer toward Earth. A few even tie it to ancient prophecies or secret programs. None of it is grounded in evidence. It's a symptom of how complex science gets warped when it travels through social media filters. The takeaway is clear. Scientists carry a responsibility not only to discover, but also to communicate, to clarify what's known, what's suspected, and what's speculative. Dr. Loeb has faced criticism precisely for this reason. His comments about a 30–40% chance of a non-natural origin were quoted out of context and amplified beyond recognition. His half-joking remark about taking vacations before October 29th became, in the hands of online rumor, a dire warning. To his credit, he's repeatedly stated that 3I Atlas is most likely a natural object, but those disclaimers often vanish as ideas pass from research papers to media headlines to viral posts. That's the challenge of modern science communication. In an age where information moves faster than nuance, context is the first casualty. The truth about 3I Atlas sits somewhere between the extremes. It's neither an alien craft nor a meaningless rock. It's an extraordinary natural visitor, an object that deepens our understanding of how worlds form and evolve across the galaxy. It deserves our focus and our research, not our panic. It's not a threat, not a probe, not an invasion. It's a relic, an ancient, peculiar, and fascinating comet from another star system, whispering stories of places we've never seen Chapter 13. What we're learning. Let's set aside the speculation for a moment. The alien theories, the doomsday talk, the what. When we strip away the drama and focus purely on the science, what have we actually learned from 3i Atlas? Lesson 1. Interstellar objects are diverse. We can no longer assume all interstellar visitors will resemble the comets and asteroids native to our solar system. Every planetary system forms under unique conditions, with its own chemistry, temperature ranges, and physical makeup. The fragments ejected from those systems reflect that diverse 3i Atlas is rich in carbon dioxide, which suggests it formed in a region where CO2 ice was more stable than water ice. That clue alone tells us something profound about its birthplace, the temperature, the pressure, and even the chemical environment of the star it once orbited. It gives us a peek into the ancient conditions of a planetary nursery billions of years old, light years away from our own. Lesson 2. Old objects behave different. Most comets in our solar system are relatively young, a few billion years old, preserved in cold storage within the Kuiper belt or the Oort cloud. Shielded from radiation, they've remained largely unchanged since the dawn of our system. 3i Atlas, on the other hand, may be 7 to 10 billion years old. It has wandered through interstellar space for eons, bombarded by dust, scoured by cosmic rays, frozen and thawed by passing starlight. That endless journey likely altered its internal makeup, fractures, layers, regions of differing density and porosity. So when such an ancient traveler suddenly finds itself heated by a sun again, it may react in unpredictable ways, abrupt outbursts, erratic gas jets, or fragmentation that defies our usual model. Understanding those effects matters not just for interstellar visitors, but for unlocking the hidden history of the oldest bodies in our own system, the ones that predate Earth itself. Lesson 3. Chemistry can be strange. One of the most intriguing findings has been the apparent presence of nickel without iron, a chemical oddity that challenges our current models. Could nickel and iron separate through selective sublimation? Could nickel carbonyl naturally form in the vacuum of space? Questions like these expand our understanding of cosmic chemistry. They matter deeply for astrobiology, the study of life's origin. To trace where life's building blocks come from, water, organics, minerals, we must grasp the full range of chemical reactions that can unfold in planetary environments. Every peculiar discovery widens that range and refines our models of how life-bearing systems might emerge. Lesson 4. Size distribution matters. 3i Atlas is large, far larger than the two interstellar objects detected before it. This fact alone raises key questions. Are massive interstellar wanderers truly rare, or are we just more likely to notice them because of detection bias? Could there be countless smaller ones passing unseen? The answers could reshape our understanding of planetary formation throughout the galaxy. The distribution of ejected object sizes reflects the population of planetesimals that formed within their original system. By studying what gets expelled, we learn what remained, the building blocks that formed worlds. Lesson 5. Trajectories are instructive. The fact that 3i Atlas approached from the galactic core's direction, moving roughly along the galactic plane, reveals clues about both its ejection mechanism and its long interstellar journey. It wasn't cast adrift by chance. Its path has been sculpted by gravity over billions of years. By retracing that trajectory, charting the stars it once passed, and modeling the gravitational influences that altered its course, astronomers are essentially performing forensic astronomy, using present-day evidence to reconstruct ancient cosmic events that took place trillions of kilometers away and eons in the past. Lesson 6. Coordination works. The response to 3i Atlas proved that the global astronomical community can act as a unified system when faced with an urgent celestial target. Observatories across continents collaborated in sequence as Earth rotated, while space-based telescopes, including Hubble, JWST, and orbiters around Mars, were redirected to capture key data. Even amateur astronomers worldwide contributed invaluable observations, all of which were rapidly exchanged through digital networks. This level of international coordination is more than a success story. It's a rehearsal for the future. As interstellar detections become more frequent, every new visitor will offer a brief window for study. To make the most of those chances, we must continue to mobilize quickly, observe efficiently, and analyze deeply. 3i Atlas has become our first real test case. And overall, humanity passed, not flawlessly. There were communication gaps, scheduling delays, and a few missed opportunities. But in general, the collective effort was remarkably effective. Lesson 7. Public interest is immense. The story of 3i Atlas has captivated far more than the scientific community. Millions have followed its passage across the sky through social media debate, news reports, and speculative discussions. That fascination is valuable. It opens doors for education, fosters global curiosity, and reminds people that the universe remains vast, unpredictable, and full of wonders. Yet it also brings responsibility. Scientists must communicate clearly, separate speculation from confirmed data, acknowledge uncertainties, and draw clear lines between what is intriguing and what might sound alarming. In many ways, we've been reminded that how science is shared can matter just as much as the discoveries themselves. These lessons aren't theoretical. They shape how we'll handle future interstellar objects, design detection networks, assign telescope priorities, and engage the public in meaningful ways. 3i Atlas has already made us more coordinated, more careful, and more curious, and those improvements will serve us well, because this, truly, is just the beginning. Chapter 14. The Future of Interstellar Astronomy. On a crisp, clear night in 2026, the Rubin Observatory in Chile will begin capturing its first all-sky survey images, and this moment will redefine observational astronomy. What makes Rubin revolutionary isn't its mirror, impressive at 8.4 meters, nor its colossal 3.2 billion pixel camera, the largest ever built for the cosmos. Its power lies in what it will do with those tools. Every 3 nights, Rubin will photograph the entire visible sky, every galaxy, every star, every object that can be seen from Earth. By comparing each new image with the previous ones, it will detect anything that shifts or changes: an asteroid crossing a star field, a distant supernova erupting, a variable star flickering, or perhaps an interstellar traveler gliding silently through our solar system. Current estimates suggest that Rubin could detect between 1 and 10 interstellar objects each year, possibly more as its algorithms improve. Within a decade, we might have a catalogue of hundreds of visitors from beyond our star system, each carrying physical and chemical signatures of faraway stellar nurseries. Some will be tiny, dark, and hard to analyze. We might only learn their brightness and basic trajectory. Others will shine bright enough for detailed spectroscopy, polarization studies, multi-wavelength imaging, even radar mapping if they venture close enough to Earth. A select few may display behavior or chemistry so strange that they earn the same level of scrutiny as 3i Atlas, and perhaps one day we'll encounter an object so anomalous that no natural explanation fits. That's why preparing frameworks for identifying artificial interstellar objects is crucial, not because we expect them, but because we must be ready if we ever find one. Traditional SETI, Search for Extraterrestrial Intelligence, focuses on detecting radio signals, deliberate broadcasts from other civilizations, but interstellar objects provide a different opportunity, searching for physical evidence instead of messages. This approach, known as artifact SETI, holds distinct advantages. Radio transmissions fade with distance, dispersing until they blend into cosmic background noise. Even powerful transmitters might only be detectable within a few hundred light-years, but a physical probe once launched endures indefinitely, a silent traveler gliding through the void for millions of years. If one happens to pass through our solar system, we can see it no matter how ancient its origin. The odds of any single probe crossing our system are incredibly small, but scale matters. If technological civilizations are common, and each sends out countless automated explorers over millennia, the galaxy could contain billions of artificial objects drifting among the natural one. Even with such a small ratio, the number isn't zero, and as our detection tools sharpen, we might just find one. The real challenge is knowing what to look for. Thanks to 3i Atlas, Our understanding of detection criteria has evolved. Trajectory alone can't prove anything. Gravity can produce complex paths naturally. Chemical composition alone isn't proof. Exotic materials can arise from extreme environments. Size, shape, or activity alone can mislead. Comets and asteroids can act unpredictably. Instead, the key lies in combinations of anomalies, intersecting traits that together resist natural explanation. And even then, humility is vital. Astronomy's history is filled with discoveries once mistaken for alien signals. Pulsars, for example, were initially dubbed LGM for little green men, before being recognized as rotating neutron stars. Quasars, too, seemed artificial at first, until we understood they were powered by supermassive black holes. The lesson is timeless. The universe often looks stranger than it is, until we learn its language.